Hello everyone, my name is Hussain and welcome to DSAdaddy. In this video, we are going to discuss that why the time complexity of sorting algorithms cannot be less than of nlogn. Why nlogn is the lowest bound that is applicable to them. Okay. Now, before starting the video, I just want to clarify that there are two sorting algorithms, namely counting sort and radix sort. Okay. Now, these two sorting algorithms can sort the list of numbers in of n time, okay, which is obviously less than of n log n. But the problem is that these are ranged sorting algorithms. Okay, so these are range sorting algorithms. Range sorting algorithm means that they can only work if the input elements are in a specific range. Okay, so for example, if the input elements are from 1 to k, then counting sort will work perfectly. And if the input elements are from 1 to n square, then radix sort will work efficiently. But what if I want to sort an array where the number of elements are random? Okay, so for example, if this element is 10 to the power 6, this is 1, this is 20, this is say 200, and this is, let's say, 2 to the power 100. Okay, like these numbers are random, and obviously these numbers are not in 1 to k or 1 to n square, they are beyond them. So which algorithm will I be using, and is that even possible to find an algorithm which can sort this array in of n time? Okay, so we'll find out this in this video. Let's take an array, and that array is 1, 4, 3 and 2. Okay, I have to sort this array, and the sorted array would look like 1, 2, 3 and 4. Okay, so far so good. Now I have to devise an algorithm which takes of n time and which can sort this array. Okay, I have to find out whether this is possible or not. So starting out, we can say that this sorted array is basically a simple permutation of this array. Okay, I hope you all know what permutation means. Permutation just means that when we try to obtain something out of when we try to obtain an array from another array by just repositioning the elements, then we can say that the second array is a permutation of the first array. Okay, so in a way it can be said that the sorted array is a permutation of the given array. Okay, let's try to write some more permutations. So we are given 1 4 3 2, right? So 1 4 3 and 2 is the input, and let's write some permutations of the same. So we have 4 1 3 and 2. Okay, then we have uh, 1 4 3 uh, 1 4 3 2, yeah, 2 1 4 3, and at last we have, let's say, 3 2 1 4. Okay, so these are the three permutations that we have. There can be many other permutations. If there are n numbers, then the number of permutations are n factorial. Here the number of elements are n, so the number of permutations are 4 factorial. Okay, now I'll be devising a comparison based sorting algorithm. Why am I saying that? Because comparison based sorting algorithms are known to have the least sorting complexity. Okay, for example, if I take the example of merge sort, then merge sort can sort the array of n log n time. Okay, and similar is the case with quick sort. Okay, because these two algorithms can sort the array in of n log n time. Okay, so my approach will be to devise an algorithm which is comparison based. Okay, because then I will be having the possibility of low time complexities. So let's try to compare the elements and find the algorithm. Let's try to compare these two elements, 1 and 4. Okay, 1 comes before 4, which is the right order. Okay, and I also want that in the final array as well, in the final sorted array. So amongst all the permutations, I only want those permutations in which 1 is coming before 4. Okay, 1 will come before 4 obviously, so I'll cancel out all other permutations in which 1 is not coming before 4. Okay, so here if I say the first permutation, 4 is coming before 1, so obviously this permutation is not going to be a sorted one. Okay, right, So I'm going to cancel this out. If I see this permutation, then here 1 and 1 is coming before 4, which is perfectly fine. Here also 1 is coming before 4, which is perfectly fine. Okay, so in all we cancel out one permutation. Now let's try, and other permutations will also be cancelled because there are in total 24 permutations of this array, but I've just listed down 3 permutations. So other permutations will also be cancelled. Okay, let's try to compare now these two elements, 4 and 3. 4 coming before 3 is also absurd because 4 cannot come before 3 in the sorted array. So I'll cancel out all the permutations in which 4 is coming before 3. Okay, so let's say that we have another permutation 2, 4, 1, 3. Okay, now in this permutation 4 is coming before 3, right? So this permutation is also not sorted. Let's cancel this out. Here 4 is coming before 3, that's perfectly fine, and here also 4 is coming before 3, so that is also cancelled. So in all, what I want to mention here is, if there are n factorial permutations, then in each step you're going to cancel some permutations, and those cancel permutations are exactly n factorial by 2 or asymptotically n factorial by 2. Why am I saying that? Because let's say you have this array. Okay, you have 2, 1, 4 and 3. In almost half of the arrays, if I'm comparing these two elements 2 and 1, in almost half of the arrays 2 will be before 1, and in another half arrays 1 will be before 2. Okay, so this is the asymptotic notation, which says that in almost half of the arrays the first element will be before the second one, and in other half arrays the second element will be before the first one. Okay, so in the first comparison, that is between 1 and 4, half of the permutations will be cancelled. Okay, because obviously in those permutations which will have 4 before 1 will not be accepted. Similarly, in the second comparison 4 to 3, half from the remaining half will also be cancelled. Okay, so the remaining were n factorial by 2, another half, that is n factorial by 4, will also be cancelled, so you will have n factorial by 4 remaining. And similarly, we will compare every element with every other element. So in all, with every step the number of permutations will go on decreasing. Okay, and a time will come when you will have only single permutation left. Now by using common sense, it is obvious that this is going to be the sorted permutation. Why am I saying that? Because this is the only permutation in which all the elements are in the right order. That is why it came in the last moment. Okay. Now what I have to do is I have to start from the unsorted array and I have to end at the sorted array. That means I have to start from all the n factorial permutations and I have to reach to a single permutation which is sorted. Okay, and I have to find the time complexity of doing that. So what would be the time complexity? Obviously the number of steps that I've taken. Okay, let's say the number of steps are x. Okay, we don't know what x is, and we'll find out now. Okay, so x basically is what? That is the number of steps which the algorithm has taken to reach from n factorial to 1. Okay, so suppose you have 16. To reach from 16 to 1, what you will do? You will divide 16 by 2, then by you will get 8, divided by 2 will get 4, divided by 2 will get 2, divided by 2 will get 1. Okay, so you took 1, 2, 3, 4 steps. Okay, which was log of 16 base 2. Okay, similarly, to reach from n factorial to 1, you will take log of n factorial steps. To reach from n to 1, the compiler will take log of n factorial steps. Okay, so the total number of steps are going to be log of n factorial. Okay, now what log of n factorial can be? Okay, let's try to solve this. Log of n factorial can be log of n into n minus 1 into n minus 2 into n minus 3 and so on. Okay, till 1. Now this can be written with simple mathematics as log of n into n minus n plus log of n plus 1, because we know that log of a into b is log of a plus b, right? This is log of n minus 2, this is log of n minus 3, and it continues all the way to log of 1. Okay, if you see, there are n logs here. Okay, and all of them are asymptotically equal to log of n only. This is also equal to log of n, this is also equal to log of n, and this guy is also equal to log of n. Okay, so the total time complexity is n log of n. That means the total steps are n log of n. Okay, here the total value of the total number of steps were log of n factorial. We simplified them using mathematics and we reached n log of n. So n log of n is the total number of steps which the compiler will take to reach from the n factorial permutations to a single permutation that is sorted. Okay, our goal was to devise an algorithm which can sort this array in of n time. Obviously, of n time is not the answer. Instead, we reached at the time complexity of n log n. That means that our theorem is contradicted here. We cannot reach to a sorting algorithm which can sort the array of n time, given the array elements are random. Okay, so this proof concluded that the least possible time complexity of any sorting algorithm is n log n, and you cannot do better than that. Okay. Apart from that, we also have another explanation, and this explanation is a bit intuitive one. Let's say we have an array. This is 2, 1, 4, and 3. I'm asked to sort this array. Okay, so the sorted array would be 1, 2, 3, and 4. Okay, now if I want to write down these numbers, how will I write them? I will write 2 as, like, number of digits in 2 is what? The number of digits are 1. Say similarly, if I have a number n, then the number of digits would be log of n plus 1. Okay, say for example n is 1000, but the number of digits are log of 1000 plus 1, that is 4. Okay, you can do this with any number and you will reach the same conclusion that the number of digits in any number can be minimum log of 1000 log of n plus 1. Okay, this thing. So in order to even write a number, you have the compiler will take log n time in order to even write a number. Okay, and because there are n numbers here, just forget the sorting. In order to even write the number, okay, what you will take? You will take log n time, and there are n numbers in the array, so there would be log of n. Okay, suppose the number of digits are d here. Okay, so that would be log of d. So log of n log of d. Okay, now so what if the number of digits are equal to n? For example, if the size of the array is also n and the elements are having n digits, for example it is n and it is 2n, 3n, 4n, like 5n and 6n, so these are the array elements, so they are also having the same number of digits, right? Asymptotically the same number of digits, so d can also be equal to n in the worst case, so the time complexity can be n log n here as well. So this theorem also proves, or this explanation also proves, that the time complexity cannot be better than n log n of any sorting algorithm. In the first explanation, we used pure mathematics. In the second explanation, we used an intuitive approach. Okay. So these two algorithms disprove our initial question, that whether answers our initial question that whether there can exist a sorting algorithm which can sort an of n. That is not possible, because even to sort an array, because even to just to put an array element at the right place, you would require log of n time. So yeah, that is it. I hope you were able to understand why the sorting algorithm is of n in the best possible case, and thanks for watching.